extent in Antarctic. And you would see that until the mid-2000s, the situation has been very stable with a time series that look a bit like white noise. And what has happened since then is very puzzling. We've had first a period of rapid increase of sea ice extent until the mid-2010s, and then since then a rapid, sharp decrease of sea ice extent that yet remains to be explained. So this is really the signature of perhaps something going on in Antarctica. We have increase in variance. We have apparently longer persistence in the sea ice extent anomalies. So there is hope maybe for more predictability than what we used to have in the past. But also when we look at the maps of sea ice anomalies, we see that the trends have very strong regional patterns with increases in the Weddell Sea, decreases in the Ross and Amundsen sectors. And all in all, that gives the motivation for trying to see if we can forecast those anomalies in Antarctica. So that's the first motivation, I would say. The second one is more operational. There is a growing activity in Antarctica from scientists, of course, but also from tourists. There's a boom in touristic activity. And people tend to forget that this is a very harsh place and a very dangerous place. I can tell you the story of a ship, Brazilian ship that left Brazil in 2012 in April, and so he shipped all the way down to Maxwell Bay. I think it was for a research expedition, and then the ship got locked in the ice very quickly. The ice crushed the ship, and the ship wrecked at the bottom of the sea. And fortunately, there was no casualty. All the crew was rescued. But this is to remind us that sea ice in Antarctica can grow very quickly, can be very dangerous, and these are very hostile waters. Nowadays, what we have in terms of sea ice information is what we call ice charts. So these are sort of maps that classify the ice in different sort of regime with closed ice, fast ice, or open drift ice, etc. But today there is no real sea ice information a few weeks or a few months in advance, and so that was the second motivation to try to deliver such kind of information. The last motivation is more personal. I have been quite involved since the late 2000s when I started my PhD in the topic of polar prediction. You can read a blog article that I authored last year, two years ago, explaining that pretty good progress has been made in predicting polar climates from weeks to seasons. And in particular, there has been a very strong progress in predicting the sea ice in Arctic, thanks in particular to the Sea Ice Prediction Network. And this growing activity, you can see it by recording the number of publications that have in their title polar or Arctic or Antarctic or Southern Ocean prediction. And you would see there is a really an exponential increase in the scientific activity around that theme. But still, for the Southern Ocean, it's quite limited. And so I wanted really to fill a gap by coordinating the scientific activity around the topic of sea ice prediction in the Southern Ocean. So CIPIN South was born. It was in 2017. And CIPIN South has three objectives. One is to collect all possible forecasts in the Southern Ocean and to identify the groups that do such predictions. The second one is to test the skill of those systems compared to trivial forecasts like climatology or persistence. And finally, we would like to try to understand what are the causes of model error and to improve the forecast, of course, in the future. The question that you might have is Antarctic sea ice really predictable? And that would be an entirely legitimate question because, as probably most of you know, Antarctic sea ice is highly seasonal. So it grows during the winter. The ice edge, you can see on this satellite picture, is quite vast. But in summer, ice extent almost shrinks to zero. There's only patches of ice remaining in the Weddell Sea, sometimes in the Ross Sea, but it's quite limited. So the question could be, what is the hope for seasonal prediction if the ice is almost seasonal? Well, people have started to look into that almost 10 years ago. The first study that I know was from Marika Holland and colleagues from the NCAR. And what they did is that they ran a coupled climate model, the CCSM. They added tiny perturbation to an ensemble of initial state predictions, and they wanted to know when predictability from initial value, from initial conditions would be lost and would disappear, essentially. And what you see on the right is the prognostic potential predictability. So it's a measure of predictability, with 1 meaning lot of predictability and 0 meaning no predictability at all. And you see that as a function of time. And what should be striking to you is that the signals tend to propagate eastward, and of course tend to propagate in time. And what is really interesting is that you can cross the limit of a season and you can still have predictability well beyond 1 year or even a season. So that was the first study to look into that. Another study that I really like showing is again from Marika Holland, where they showed that there is a strong correlation between the zonal winds anomaly in the Western Ross Sea and the sea ice area in that region. And the mechanism is quite simple. When you have strong winds, you increase the ice divergence, you increase the shortwave heat absorption into the ocean, and then you delay the sea ice formation in autumn, and therefore you have a sort of long-range mechanisms of predictability from basically October until March or April the next year. So that was a second evidence for such mechanisms. Other studies have looked at climate models, and one robust mechanism that has emerged is what is called the re-emergence of winter sea ice predictability, thanks to the storage of information below the mixed layer. So this graph shows the point correlation between sea surface temperature and potential temperature at different depths as a function of time. And the reference is taken as September month 0 here. And what you should see is that correlations, so indicated by the red areas, the correlations can really penetrate below the mixed layer limit that's shown with the dashed line, and then resurface a couple of months later. So the idea really is that whatever heat is stored in the ocean or even below the mixed layer can really emerge and set the presence or not of ice a couple of months later. There's been a recent study by the team of Will Hobbs and colleagues showing also predictability in the access coupled model, and also a study of operational sea ice skill in the S2S, so subseasonal to seasonal data set. And then I finished because the advantage is that there are not too many studies about that. There was a study by the GFDL team. Mitch Bushuk and colleagues show basically that yes, there is skill, and a key mechanism of predictability is the zonal advection of upper ocean heat content anomalies. So if I have to summarize these studies, I would say yes, there definitely is predictability in Antarctic sea ice, well beyond actually the seasonal timescale. Critical is the role of zonally advected upper ocean heat content anomalies. And what studies have shown also is that the predictability estimates do depend on the vertical stratification of the models. So those models that produce very deep convection and that have also very deep mixed layers tend to have longer predictability than those that have very shallow mixed layers. So it's also a message that it's important to constrain those models by, if we have it, by the observed stratification. So how does CPIN South work? Well, the protocol is actually pretty simple. What we do every year is that we first publish a call for contributions. We send an email to the many mailing lists, and we have a website also where we say, okay, we are in November. You are now able to submit your forecast. The forecast have to start on the 1st of December of each year, and they cannot use data after the 1st of December of each year. So that's the end of the spring in in the Southern Hemisphere. So people submit their forecast, and we just request that at least people submit total sea ice area, so the area of ice integrated over the whole domain, at the daily resolution. We want to have the daily information to be able to compute fine statistics on the output. We allow and we really encourage people to submit not just one forecast, but many of those. Ensemble forecasts are much welcome. So we have a lot of groups, including people providing dynamical forecasts that are submitting up to 51 ensemble members, and that really allows sampling uncertainty related, for example, to the weather variability, or even to the uncertainty in initial state. And then we wait for 3 months, and in early March, we download the observational data, we compare the data to observations, and we assess the skill of those forecasts. To give you a bit of idea of who are the contributors, this is the list of the contributors for the last summer season. We had 15. That was a record high in terms of contribution. And you see that there are essentially two groups, people doing what we call coupled dynamical or forced dynamical predictions. So these are based on process-based model, typically ocean, sea ice, physical models that are even coupled to the atmosphere. So based on the first principles of conservation of mass, energy, etc. But we also have an increasing number of statistical contributions. And by statistical, we mean those groups that look at past observational data, and they train their own statistical model by doing regressions, classification, any sort of machine learning approach to to learn something about the system and to apply the same rule on the coming season. And so these are what we call the statistical contributions. The first diagnostic that we make normally is the total sea ice area. It's probably the most stupid diagnostic we can make, but still it's quite useful to see if nothing is going wrong. So that's the total area of sea ice around Antarctica, starting on the 1st of December, ending 28th of February, and observations. And what we usually notice, and that's been a pattern that has been quite frequent over the past years, is that the dynamical models really struggle capturing the initial state. They have this very large bias already at day one of the simulation for reasons that are still not fully clear, but the fact is that it's pretty difficult to constrain a fully coupled model to be close to any sort of observations because the model has its own biases. And even if you force the state to be the observed state at day one, then in a couple of hours or time steps, the model can really bounce back to its own climatology. So that's one hypothesis to explain that dynamical models tend to start normally very biased high. When we look at the minimum in summer, normally the distribution of forecast is doing quite good compared to observations, in the sense that it brackets the observations. But of course, if it's good on the right and if it's not good on the left, it means that something must be happening in the middle. And what we see is that the dynamical models, they tend to overcompensate the initial bias by producing excessive melt rates between the 15th of December and the 15th of January. Then we go a bit finer, and we looked at the data in a more systematic way. This figure takes a bit of time to process, so let me browse you through the figures so that we are on the same page. On the left, you see here the 1979 to 2015 climatology. So that's the distribution of all observed February mean sea ice area in Antarctica by observation. So it's a PDF, giving a mean and a standard deviation, if you like. And then we have 5 years for which we have a prediction. For each of those years, we have, of course, verification data in black, and you can see that the observations, we have 2 observational data sets. We have observations that lie on the low side of the distribution because the previous years have been quite low, as you have seen in the first graph. And then we have the SIPIN South ensemble. So it's the distribution of the 15 or even sometimes less forecasts that we receive by all the groups contributing to the exercise. And we have a median. I mean, it's a usual box plot. We have a median. We have a 25 to 75% interquartile range, and then we have a 95 to 5% confidence interval. And the circles are the outliers. And the bottom line of this figure is that, well, you see that the SIPIN South ensemble, so the box plots, do capture, I mean, are on the low side of the climatology, and there is no real year where you could say that the observations are statistically incompatible with the SIPIN South ensemble. So it's pretty good news that as a whole, as a group, the SIPIN South forecast, they tend to bracket these observations. Of course, we want to know if that happens for the right reason, and we can reproduce this analysis at the regional scale and by breaking down the sea ice area per sector. So we have divided the Southern Ocean into 5 sectors: the Weddell Sea, the Indian Sea, the West Pacific, the Ross Sea, and the Amundsen-Bering Southern Sea. And the bottom right is the figure I just showed. And if you do this analysis by sector, you would see that the same conclusion holds as the one I just mentioned. So observations are compatible with the forecast distribution of the models, except maybe for one region, and that region is the Ross Sea. In the Ross Sea, we see that systematically the SIPIN South ensemble has overestimated the observed sea ice area. We have a couple of hypotheses there. It could be that the Ross Sea is an area where the weather variability is really strong, and that means that predictability is actually lower in that region, and models simply cannot capture these anomalies. Another explanation that I got from Paul Holland, I don't know if he's in the room, but so he works at the British Antarctic Survey, is that the models can't really capture the landfast ice or the ice close to the coast that is getting very thick in the Amundsen Sea, and that gets advected into the Ross Sea in the summer. So that's maybe an hypothesis we would like to test. There's a way to quantify the mismatch between the observed and the forecast ice edge spatially, and that way is called the integrated ice edge error. It's a measure of all the small patches of ice where you have a disagreement between a forecast and an observation. So in that case, you would, if you have a forecast in red and an observation in green, you would count all the areas where you have observation but not forecast, or where you have forecast but no observation. And then you can sum up all these areas and come up with a number that gives you the area of disagreement between your forecast and observation. So we ran that on the SIPIN South ensemble, and one really interesting pattern has emerged. That pattern is that the statistical model contributions, so these are in orange, they tend to have a much lower error than the dynamical model contribution. So we have here a key message is that when it comes to the spatial distribution of sea ice area, well, the statistical model contributions, they seem to outperform the dynamical model contributions, and that's a really strong result that we have seen being repeated over the past years. Now, a question that I would like to raise, and that's maybe a question for debate. We can talk about that later. I would be curious to hear about your opinion. Is what do we prefer? Do we prefer to have a model that, like the dynamical model of the metaphysics here, that has biases? So you see the observed ice edge is in white, the simulated probability of ice presence is in color. There are clear biases here. You have ice here in the Rossi at very limited locations, but the model says that there could be ice basically all over the place. Do we prefer to have that? So quite a lot of uncertainty, but let's say on average it's okay. Or do we prefer to have a sharper forecast? By sharp, I mean with more confidence, but that have then areas where there is a risk of false alarm. So you could have ice where you didn't predict ice in fact. And it all comes down to the question of, do we prefer to have, well, if you play darts, for example, do you prefer to have your darts that go on average close to the center but are quite spread, or do you prefer to have them all accurate, so at the same location but quite far off the center of the board? There is a way that we can try to quantify that using a beautiful theory from forecast verification. I don't know, I guess there are some forecast people in the room because you're doing polar meteorology probably. There is a tool to measure the balance between the bias and the variance in a forecast. It's called the continuous rank probability score. The idea is pretty simple. Suppose that you have a metric that you would like to forecast, so sea surface temperature, for example. You have an ensemble of predictions from a model. So this is the blue Gaussian curve here, and then you have some observation in dash. Well, what you could do is that you take the cumulative distribution function of your forecast, the integral of the probability density function, and then you measure what is the area in between the forecast CDF and the verification data. And the larger the area, the worse the forecast. What we need to understand is what does the continuous rank probability score measure? Well, it measures the forecasts that are biased, of course, because if you bring that blue curve to the left or to the right, then of course the blue area will increase a lot. But it also penalizes the models that have very large, very wide distribution. Suppose that you have a forecast PDF that goes like this, then the area of mismatch between observation and forecast will be pretty big because you will have a very flat forecast. So all in all, the CRPS is a way to measure the skill of a forecast, balancing the bias and the uncertainty in the ensemble that you are provided. And we applied the CRPS to the 15 predictions that we got. And interestingly, when we run this forecast, we see that the dynamical forecasts are not doing too bad. So low values mean that we have better skill. So this is let's say the best of the forecast for total sea ice area. It's a dynamical model from the Canadian Center. Then we have a statistical model that has performed very well over the past years. We have again a dynamical model, again a dynamical model. And what the message I would like to pass over here is really that, yes, dynamical models do have a large spread, but this spread is somehow reflecting their genuine uncertainty about what they are trying to forecast. While there are some statistical models that 1 year might be spot on, but the next year could be totally off. And this will be highly penalized by the CRPS skill score. I will finish by, well, quickly mentioning that SIPIN South is yes, evolving quite quickly. It's a quite fascinating journey for me and for the participants to that group, because we have a growing number of participants. We have growing number of input data. There seems to be some momentum around that topic. People get really interested in contributing. Yourself, if you would like to contribute, it's pretty easy. I will explain how. But if you feel the spirit of a forecaster, don't hesitate to join the crew. It's quite fun. We have run a special forecast for the year of polar prediction Southern Hemisphere special observing period. So that's a period extending from May 1st to August 31st. We would like to test whether the skill is better or worse during the growing season compared to the summer, and we have received so far 7 predictions. I think an 8th one is coming. And the pattern that I tried to explain about dynamical models overestimating the initial state seems to be valid again, at least for all prediction at UCL. But it will be interesting to see what will be the evolution of the time series of observation, to see if the ensemble again brackets the observations in autumn. I'll finish by saying that SIPIN South is entirely open and public. There is a GitHub repository where all the data, all the time series that I showed, all the scripts that were used to make the figures are available, and you are highly encouraged to use it. Also you can find on the SIPIN South website the call for contributions and how you can submit your own forecast if you like to. So in conclusion, I would say that Antarctic sea ice prediction is really emerging as a very hot topic for polar research, I believe, because of the societal need and the interest of many people for that variable, and it's becoming really important to try forecasting sea ice conditions. There is some good evidence about potential predictability of sea ice in Antarctica. There are definitely biases and widespread in the predictions, but still, I mean, after 5 years of doing this exercise, I would say that there are level of skills that I didn't really expect when I started this. When I started SIPIN South, I would say that I was pretty confident there would be no real skill in the system, but there seems to be some skill in the end. But still, when you look at the regional scale, there are regions like the Ross Sea where a lot of work remains to be done. With this, I guess I will leave it there, and I would open the floor for questions and for discussion, of course. Thank you.
All right, thank you, Francois. That was a great presentation. Yeah, I think this is a good moment to open up the chat. So if anybody has any questions for Francois, comments, or anything they want to say, now would be a good time to unmute yourself.
Good morning. Can I go first?
Sure.
This is Alvaro from Argentina, from the Naval Hydrographic Service. Hi, Francois. Thank you very much for your presentation. It was great to see all the efforts and the improvements on sea ice modeling. And I have sort of comments and 1 or 2 questions. The first comment is that we really need an increase on sea ice observations in Antarctica to have a better knowledge of the increase and decrease of the sea ice edge or sea ice field. We have, as you mentioned, every year more and more tourist ships, especially in Antarctic Peninsula, but we really don't know if all those ships are in areas surrounded by sea ice or not. And that's a difficulty for the ICE services that need to provide ICE charts or forecast. And the other thing is to comment is that we also need to have, I'm talking as a polar meteorologist, we also need to have operational forecast on sea ice. As users of forecast, we need to have the best way to access the information. The Sandra Barreira forecast, we are trying to improve the visualization, for example, of the information, that all forecasts can access the outputs of the model and have the best interpretation of the information. And my question is, what's your opinion on that slide that you show about accuracy, and what do we need to, that one, yes.
Yeah.
What's your opinion about on accurate or precise? Because I guess that we still far away from accurate and precise. So I guess that precise is better, but maybe not. And I would like to know your opinion on this particular matter. Thanks.
Yeah, well, thanks for your comments, and I would agree, of course, and thanks by the way for having contributed with your group for so many years. I understand that you are working with Sandra.
Yes, of course. Yes.
Yeah. So yeah, about conveying sea ice information, I think you raise a very good point, and that's one of the missions of Sipping South is to try to see if that kind of map is relevant and is useful for users. So I didn't explain that map very well, probably because I was maybe going quickly over it. But the idea is that when we have multiple ensemble forecasts, like here we have 42 for each grid cell, and for each day of the period that we have, we can count the number of those 42 ensemble members that would simulate the presence of ice, and presence could be more than 15% of ice concentration. And then you end up with a probability that there will be ice in a given pixel at any given day. And a key question that we have for people doing operations there is it the kind of information that that you need, or is it something that you can make use of? Because I, as a scientist, I have the feeling I can understand or I can interpret what is a probability, but maybe for some people it's not an obvious map. To answer your question, whether I prefer to have something precise but not accurate, or biased but less more accurate but more spread, I think I prefer to have something more uncertain, so more widespread, that is on average correct, than having something very confident but that is off. And the reason is that, take the right forecast here by Nico Soon, and look, for example, at I don't know if you see my cursor, but look at the Rossi here. You have the model saying that there will be no ice. Okay, it's green, so it means probability of ice presence is 0. And the fact is that there turned out to be ice in the observations because there is white contour. So it's a high risk. It's a sort of false alarm. No, it's not a false alarm. It's a false, how do you say, false negative? I always confused. But basically, you could send ships for a mission, and then they would come and they would meet ice, and they would have to turn sideways and come back to New Zealand or to whatever country. And so that's a really dangerous approach to have a very confident forecast and that have biases. I prefer to have something more probabilistic that is on average correct.
Yes, that's perfectly clear. Thank you very much, Francois.
Cool. I see David Bromwich just raised his hand. Dave, you want to unmute yourself?
Okay. Thanks a lot for a very nice talk, Francois. The question I've got is, your metric is sea ice conditions observe from space, the passive microwave inferences. So I'm wondering, sort of along the lines of the last question about, how closely what we can observe from space matches what's there on the ocean, and therefore, in judging how the models are performing.
Yes, thanks, Dave. I guess that observation from satellites really struggle near the coast because they have much difficulty discriminating between fast ice, between actual sea ice. And when you look at the products, there are flags stating where the product distributor is confident about his own product and where it's not. And the areas that are probably the most relevant for people, so near the coast, are actually the ones where you have a lot of error, but also because you have contamination of errors by the land. So the signal that you sense from satellites is polluted by the presence of land. And so this can really introduce error. So I would say probably the satellite observations are not the best products for validation. That said, if we move to higher resolution product or satellite imagery, or we run into other sorts of problems. Like if you would take MODIS, for example, for the visible surface, then you would be very annoyed when there are a lot of clouds because they would make the observations very difficult. So I would say that the products that we are using here is more for validation in the sense of climate forecasting rather than operational. But indeed, we are probably lacking, or at least I don't know, a good product that would be more adapted for operational purposes.
Okay. Do we have any more questions? If not, I actually will ask a question. Yep. It caught my interest that you actually, one of the motivations for this project is for cruise ship operations around the Antarctic Peninsula. So is your group actually in close contact with the operators of these cruise ships, or is your product a bit too research oriented to be like really, well, useful for those who actually do operations around the, well, let's say the Antarctic Peninsula?
Yeah, so I think I didn't properly introduce the team in the SIPIN South project, but Jan Lieser and Phil Reed, these are, I mean, they're working closely with the, operational people, and so they know much better what they can expect in terms of information. But so SIPIN South is, let's say, I would say more developed towards the climate community in the sense of verification of seasonal forecasts without all the downscaling part to operations. But the long-term goal is really to lay the foundations of services for operational sea ice conditions, I would say. A bit like the Sea Ice Prediction Network North is currently doing. So I don't know if you guys are following a bit the Sea Ice Prediction North. I think I had a slide about that. So the Sea Ice Prediction Network North started 10 years before Sea Ice Prediction Network South. And now we are trying to deliver metrics like the date of ice advance or the date of ice retreat, the exposure of coastline to the open ocean in late summer. We are collaborating with people from the crab industry, fishers, trying to predict the opening of the Arctic Ocean for shipping, etc. So the spirit of SIPIN South is also to move into that direction, hoping that the predictions will become better and better over the years.
Oh yeah, that sounds really cool. Okay, do we have questions from anybody else in the audience? If not, then I guess we could conclude this seminar. And Francois, just I forgot to mention earlier that I started recording the presentation because I forgot, but most likely we save the presentation and then distribute to others who ask for it. Is that okay with you, or?
Yeah, no problem.
All right.
And I can also share the slides, maybe send them to you if you like.
No, that's fine. The recording is
Okay.
good. So in that case, I would like to thank again François Massonnet for presenting his work with us today. It's I never realized there was basically almost like a game of sea ice prediction going on in the Southern Ocean. It's actually kind of fun. And thank everybody for attending today. Just keep your ears open for any new activities from us at the ICPM, especially as the IUGG comes closer. We might have more information about the conference and stuff related to that. But anyway, unless anybody else wants to say anything or has any other announcements, I will bring this webinar to an end. I have a feeling a bunch of people have just like left their computers on anyway.
Thanks for organizing this, everybody, especially Jonathan. Very interesting presentation.
Oh yeah, it was good. And I got one request. Okay. All right, great. Good to see you, Dave. And all right, I'll put this meeting to an end. Again, thank you, Francois. And yeah, enjoy the rest of your day.
Cheers. Bye.
Thank you very much. Nice presentation.
Bye.
Oh, give me some comments in the chat. Okay.
Yeah, I'll stay until maybe the room is empty. So if there's some, maybe you have shy people that don't want to ask questions.
Well, actually, most of them were paying attention. Most people are now leaving, so sometimes you get like people like join the talks and then they leave their computer and do something else.
Yeah, I had a question, but I thought of it too late. If there was any correlation to seawater temperature and the predictability, has that data been predicted in as well or taken in?
So you mean the correlation I showed between sea surface temperature and the temperature at depth?
Yeah, I came in late, so I might have missed it. It might have been at the beginning, and that's why I requested the recording.
Okay. Yeah, so there is this correlation in climate model simulations between sea surface temperature and potential temperature at different levels, but at lag +1, +2, +3, +6 months. And you see that correlation really penetrating the upper ocean and going below the mixed layer and resurfacing, say 6 months, 1 year later, showing that the memory of sea ice presence can be stored at depth of the ocean, even though the sea ice is seasonal, and then re-emerge and set the sea ice area anomalies 1 year later. So that's captured by the models.
All right, excellent. Thank you.
And our Bryce, what's your first name? It's just
it's Robert, but it's Bruce. Bruce is my first name. Yeah.
All right, Bruce. Great. I'll have the recording saved and then I'll send it to you once I get that.
All right.
Out.
Excellent. Thank you.
I got your email address. Yeah, I'll just copy this.
Yeah, we're doing a study with the National Science Foundation for subsea cables, smart cables down in that region, in the Ross Sea area. So the Ross Sea is very important to us.
Okay, that sounds interesting.
Unfortunately, it's the most difficult area to predict, apparently.
It is, and I got to know when I can get ships in there for surveys or installations. So.
Yeah.
All right, that's cool. All right then. I guess I'll close out the meeting.
Bye-bye.
All right.
Okay, thank you. I may reach out at another date. I believe I got your contact information for the slides because we may include it. We have a follow-on study we're working on, and sea ice predictability is one of our chapters in our study. So this is all very useful information.
Excellent. Looking forward to it.
Okay, thank you.
Yeah. Good. Glad to make the connection today.
Take care.
All right, buddy.